So, well, here we study completeness property of set of reals. Outline of this lecture is following. First, we define ordered field. Then we will prove Archimedean property, which is an application of completeness axiom of set of reals. Then we prove density property of set of rational, and this is an application of Archimedean property. Okay, so let us define ordered field. Okay, so here is the definition. So definition: ordered field. So last time we have defined fields. Now, so here we define ordered field, and so here is the definition. And ordered field, an ordered field is a field if equipped with an ordered relation, so which is also an ordered set, that is if equipped with an order. So order relation is denoted by this symbol, and we read as less than, such that, so this relation satisfies the following, such that the first condition is x plus y is less than x plus z, where x comma y comma z, these are elements of f, and y less than z. So instead of for, let me write if. So this inequality holds true if x, y, z belong to f and y less than z, then x plus y is less than x plus z. And the second condition is following: x, y is greater than 0, or in other words, you may write 0 less than x times y if x, y belong to f and x greater than 0, or in other words 0 less than x, 0 less than y. Okay, and we have some more definition. If x greater than 0, or as we have written 0 less than x, so if 0 less than x, then x is called positive, then x is positive, then x is positive, or in short we write as positive. And if x less than 0, then x is called negative, in symbol minus the negative. For example, so 0 is what? 0 is additive identity of the field f. Okay. So for example, Q, set of all rationals, this is an ordered field. Now we state a theorem. there exists an ordered field denoted by script R, which has the least upper bound property, which has the LUB least upper bound property, and contain Q set of all rationals. Okay, and well, so recall what is LUB property or LUB axiom. LUB axiom says that any non-empty any non-empty set or subset of R, that is say any non-empty set of reals which is bounded above which is bounded above admits a least upper bound in R. Least upper bound in R. Okay, so this is a Levy axiom, and so this R is called the set of all reals. Is the field of real numbers. And fact, so let us summarize whatever we have in the following fact. So R, this is an ordered field with LUV property or LUV axiom or completeness property, LUV axiom containing Q. Okay, so now we move to the second item, Archimedean property. So this is an application of completeness axiom of set of all reals. So Archimedean property. There are some equivalent statement of Archimedean property. So we state the property in the following theorem. Archimedean property. Okay. So if 0 less than x belongs to R and y belongs to R, then there exists a natural number n belongs to set of all natural numbers such that y is less than nx, or in X is greater than Y. So this theorem is called Archimedean property. So well, now we prove this theorem. Proof. The proof is by contradiction. The proof is by contradiction. So we define. Suppose the statement of the theorem is not true. Suppose theorem is false. That is for every that is for every n belongs to n, we have what we have in X less than or sorry, yeah. So for all, so this is not true means what? Nx is less or equal to y for every n. So if the theorem is false, then the set A equal to in X, where n belongs to set of all natural numbers, then the set, this is subset of R, is bounded above by Y, by Y. So Y is an upper bound of this set, and this is subset of R. So here we apply least upper bound property by LUB axiom of R. We have A admits a least upper bound, and we denote the least upper bound by alpha, say alpha. Okay, now by hypothesis of the theorem, X is positive. Okay, so X greater than 0, that means what? Alpha minus X less than alpha. So alpha minus X less than alpha, this implies alpha minus X is not an upper bound. Okay. So any number which is less than alpha cannot be an upper bound of A, because alpha is the least upper bound, and this implies there exists some element we denote by n naught x in A, such that n naught x less than or equal to alpha, and this is strictly greater than alpha minus x, and this part implies alpha less than n naught plus 1 times x, but this number belongs to A, and alpha is least upper bounds anyway. In particular, alpha is an upper bound, so nx less than alpha less than or equal to alpha for all in X belongs to A. But we have this because alpha is least upper bound. So, but here what we get, alpha less than, strictly less than n naught plus 1 times x, which is an element of x. So this is contradiction. So by contradiction, we conclude the proof. Okay, this completes the proof. Okay, so this is Archimedean property. Now we move to the last item of today's lecture, which is density property. So here we apply Archimedean property. So let us go to the statement. So density property. Density property. So let us state as a theorem. Theorem density property. It says that if x less than y belongs to R, so if x and y any two real numbers where x less than y, then there exists some rational number p in between x and y. Then there exists p belongs to q such that x less than p less than y. Okay, so basically between any two real numbers, there exists a rational number. So if x is here and y is here, then in between x and y we have some rational number p. Okay, so this is a statement of density property. So we prove this theorem here. So what we have? X less than y. This implies y minus x, this is greater than 0. So now for y minus x greater than 0 and and 1 belongs to set of reals. So by applying Archimedean property, there exists some natural number n belongs to set of natural numbers such that y minus x times n is greater than 1. Okay, so in the Archimedean property in this statement, uh, so uh, we use y minus x, and for y we have used 1. Okay, so this implies ny is greater than nx plus 1. Okay, so that is nx plus 1. So in other words, we can write nx plus 1 is nx plus 1 is less than uh, ny. Okay, so let us draw a picture. So suppose this is ny, and here we have nx plus 1. Okay, so nx must be somewhere here. This is nx. So this length is 1 unit. And this implies there exists some m belongs to set of all naturals which lies between nx and nx plus 1, because this interval has length 1. There exists m belongs to n such that n x less than m or less than equals to in x plus 1. And also we know nx plus 1 less than ny, and this is less than ny. Okay. Therefore, what we have nx less than m less than ny, and this implies x less than m by n less than ny, and we denote it by p. So, so after cancelling the common factors, so this is equal to p. So x less than p less than y. So p is rational. Okay. So there exists some rational p in between x and y. This is the proof of density property. So before we stop, we have an exercise. Show that if x less than y in set of all reals, then there exists some r belongs to r minus q. This is q complement. That is, there exists some irrational number such that x less than r less than y. So this is the exercise. It says that so that between every two real numbers there exists an irrational number. Okay. So we stop here.